Okay, so now we'll be solving the last problem on the final exam on multivariable calculus at MIT. So this is problem 15 and it's worth 25 points in total. So we have a vector function, yzi plus minus xzj plus k, and let S be the portion of a surface of the paraboloid z equals 4 minus x squared minus y squared. So whenever I see x squared minus y squared in something like this, I'm always going to think back to cylindrical coordinates, and which lies above the first octant. Let C be the curve C equals C1 plus C2 plus C3, where the curves C1, C2, and C3 are the curves formed by intersecting S with the XY, YZ, and XZ planes, respectively. So let's sketch a picture on what this will look like. So this is just our coordinate axes. And then so it's going to be a paraboloid. So we'll see that it opens downward, kind of like this. And then there's going to be something like that. And so it's going to be cut off by the XY, YZ, and XZ planes. So then it's going to kind of be cut off like here and here. It's just going to stop there. And now that we've had our image, then are the three curves formed by intersecting S? Yeah, with respectively, so that C is the boundary of S. Orient S so that it's traveled counterclockwise when seen above from the first octant. So then it's going to be traveled like this. Use Stokes' theorem to compute the loop integral, the closed integral on C of f dot dr by using the surface integral over the capping surface S. So we know, so the Stokes' theorem is the integral across some closed contour f dot dr. This is just to use them in bold, but they're actually vectors. This equals the double integral along the surface of the curl of f dotted with ds, which is also a vector, and this ds is going to be the normal vector times dA, which is going to be some small element of the area. So let's try to picture it here. So if we think of this as some surface, then it's going to be like this. Then it's going to be dA. I can't really fit it on there, and it's going to have direction in the normal direction. So I'll just use this. It's going to be pointing away from the surface, and we can choose two normal vectors, pointing out or pointing in, but since this is traveling clockwise and the surface is on our left, that means it's pointing out. It would be better if it signifies this is a vector. So now first, let's compute this right here. So we can think of this as the curl equals the determinant of this matrix. Sorry about that. And it's going to be this right here for the I, J, and K component. It's just going to be the coefficients. So this is going to be YZ, negative XZ, and 1. So now when we compute this, So first is going to be this, and we get the determinant of this. So this is going to be 0, since the partial derivative of 1 is just with respect to y is just 0. And then this is going to be negative x, but then we subtract that. So this equals xi. And then we cross this, and we cross that, and we cross this, and it's going to be this multiplied by that minus that multiplied by that. So the partial derivative of 1 with respect to x is just 0. And we put a minus sign here because it goes plus, minus, plus. So it's going to be minus. This is going to be 0. This is going to be, and then we 0 minus this right here, partial derivative of yz with respect to z, and that's just y. So we minus y, j, and then we add, cross that, and we cross this, partial derivative of that with respect to x is just negative z, and then we subtract this value. Partial derivative of yz with respect to y is just z, so we subtract z, and that's going to be in the k hat direction. So just cleaning this up, and we get x I hat plus y j hat minus 2 z k hat. And what we want to dot this is this value right here. And what our normal vector is going to be. So normal vector, this is just negative the partial derivative of z with respect to x, negative the partial derivative of z with respect to y, and 1. And what we do is we dot these two together. So first we can write this in vector form. So then if we just, and what we do is we dot this with this in vector form, which is just I, y, negative 2z. And then first let's compute this. This is going to be negative the partial derivative of z with respect to x, which is going to be negative 2x, since there's a negative sign here. So this is going to be the first value. I'll just keep in the same color. 2x. Same thing with y. It's going to be negative 2y. So this is going to be 2y. It's just 1. And we dot this with x, y, negative 2z. And this equals 2x squared plus 2y squared minus 2z. And what we can, I'll just write an equal sign here. And then what we can do is we can see that this, we can substitute z equals this value. And then this equals 2x squared plus 2y squared minus 2 for minus x squared minus y squared. Now we can do a substitution into polar coordinates. So that x squared plus y squared equals r squared. And then we have that this equals 2r squared minus, and this right here is going to be negative r. So then it's going to be plus minus 8, and then this is going to be negative plus 2r squared. Sorry, there's supposed to be a square there. And then this equals 4 r squared minus 8. And then we can go back to our original integral over here. Oh, sorry about that. I'll just rewrite it down here. So that means what we want to solve is our double integral across our surface of this value, 4r squared minus 8 dA, right? But so dA is supposedly dx dy, right? But then this equals, if we use the Jacobian, this is r dr d theta, where r is going to be our Jacobian scaling factor. So what we can do is this equals the double integral across our surface of 4r to the 3 minus 8r dr d theta. And now we want to find out our bounds. But so we can see, if we just erase this picture over here. Sorry about that. That we can see that r goes from 0 to 2. And because it's cut off in the first octant, that theta is going to range from 0 to pi. So, and we can find out that it's 2 because when x squared minus y squared equals 0, z equals 4. When z equals 0, that means x squared plus y squared equals 4, and that's just the equation of a circle of radius 2 centered at the origin. So that means this is going to be r equals 0 to 2, and theta equals 0 to pi over 2. And just computing this, we get, so this is just going to be pi divided by 2 times the integral from 0 to 2, 4r to the 3 minus 8r dr. And then, sorry about that. And this equals pi over 2 times r to the 4 minus 4r squared evaluated from 0 to 2. And this equals, this is 16. This is also 16, 0, 0. So this equals 0. And that's our final solution. Just